This is our video about thermodynamics, and we're going to look at the state change and which formula we use when we go from one state of material to a different state of material. So in the state of matter, you can have a solid, and when you add heat into the solid, so if you add some heat into the solid, and heat is the letter Q, measured in energy, eventually you're going to get the liquid, so the solid is gonna melt. And when the solid is melting into the liquid, there is no change of the temperature happening. So if you have ice right here, so if this was ice, under normal conditions, ice would melt at 0 degrees Celsius. So when all the ice is melted, you're gonna get 0 degrees Celsius of water. And then you will continue adding heat. So you added heat and then you turn it into the water. If you continue adding heat, the temperature of the water is gonna increase or change, and until it is not 100 degrees Celsius, it's not gonna start vaporizing. And when it reaches 100 degrees Celsius, any heat added into the water will turn it into vapor. And then again, this will be a process called vaporization. And then you still add in heat. So you keep adding heat into the water when it is boiling, but all that heat is ripping off the molecules and turn it into steam. And then you will get a steam at 0 degrees Celsius. And that steam at 0 degrees Celsius, if you keep adding heat, it will have increase of the temperature of the steam. So there are different states at which we're going to be looking at, and different formulas that we're going to be using. So right here, when I am adding heat, so this is for heat scale. So here I'm adding heat, so that's Q. And when I am adding heat right here, at first the temperature is going to rise. So when the temperature is rising and you have a solid, then you use calculating the heat that you need to raise the temperature of that solid is mc delta T. So if the temperature is rising, then you use mc delta T. Here you go from one state to a different state. You go from solid into the liquid. So you're using the melting process. And when you're going through the melting process, there is no temperature change. So if this was ice at 0 degrees Celsius, when it started to melt, to turn into water, when you get water, it's still going to be at 0 degrees Celsius at that specific point. So right here, when you don't change the temperature, you're going to be using a different formula, the heat of fusion, and that is mH of fusion, and it has a table. And usually when you have a test, I'm going to give you the numbers for every state. And then again, you get the liquid, and that liquid, the more heat you keep adding into the system, so you keep adding more and more heat. And the temperature of the, so you see right here is temperature. The temperature is going to be rising. And when that temperature gets to the boiling point, and right here we see it is 100 degrees Celsius. So for water, it would be 100 degrees Celsius. When the state is changing from liquid into the gas, the temperature is not going to change. So if the temperature is not changing, I'm going to use Q formula, which is mH, and this one is vapor. Again, this the heat of vapor is usually also given. But where the temperature was changing for the liquid, you would use heat is equal to mc delta T. And when you get steam in here, you can keep adding heat into the steam. So you're still adding heat. Then the temperature of the steam is going to increase. So the heat you need to increase the temperature is going to be mc delta T. And another interesting fact is here you had solid. Let's say this one was ice. Then we had the specific heat of ice. Here we had liquid. So in this stage we had liquid. So here was ice. If you raise the temperature of ice to the melting point, you use the specific heat of ice. And then here was the water. If we raise the temperature of water, we use the specific heat of water. And then here we use raise the temperature of steam, we use the specific heat of steam. So let's look at some examples where we're going to be using the scale in converting, we're going from one state to another in which formulas we're using to solve the problems. So in this question, I have, so they asked me to melt 0.1 kilogram of ice. So I'm starting with ice, and they give you the specific heat of fusion or melting point to melt, heat of melt. And then I want to melt it and turn into the water at 20 degrees Celsius. So I'm starting at the melting point of ice, which is 0 degrees Celsius. Here I'm going to have the melting process, so it's going to be melt. And then I'm going to get into the water that is still 0 degrees Celsius. And then from this water at 0 degrees Celsius, I'm going to change its temperature to 20 degrees Celsius. So if I did not use, if I did not have to change the temperature, the heat that I needed here, let's maybe do this way, heat that is needed equals to, and so for this part, when we did melting, I'm going to use the heat of fusion. So I have the mass that is given 0.1 kilogram, and then I have H of fusion, and then plus, now the heat that is needed right here is with the change of the temperature. So that is going to be MC delta T, because I'm changing the temperature. And then C of the water, because I'm using the water that is heating up. So now if I plug in the numbers, I have the mass. Actually, they both have masses, so I'm going to just take the mass out. So I'm going to have the mass. And then I have heat of fusion, and plus C delta T. Okay, and now if I plug in these numbers, I'm going to have, so the mass that is given 0.1, and then the heat of fusion, usually I'm going to give it to you on the test, the numbers that you're going to see, but the heat of fusion for the ice, so here I see right here all the way at the end, the heat of fusion is 3.310 to the 5th. So I'm going to plug in 3.310 to the 5th, and then plus, and then I have water, so I need specific heat of water. So if I look right here, here is the specific heat of water, and I'm going to round it to 4200. So I have 4200, and the temperature that I have to change, I went from 0 degrees Celsius to 20 degrees Celsius, so that's times 20. And then we have, if I multiply these numbers, I get 41,400 joules. Or if you look at the PDF for the lessons, you see 41.4 kilojoules as your answer. So that's how much heat you will need to turn 0 degrees Celsius ice, which is at the melting point, into 20 degrees water. In this question, they say that we have 100 grams of ice, so that's 0.1 kilogram of ice, and they give you the specific heat of ice, which is 2060. And then I'm gonna have to turn it, and it is at 20 degrees, negative 20 degrees Celsius, and I have to turn it into 10 degrees Celsius water. So at first I take ice, which is at negative 20 degrees Celsius. I'm gonna turn it into the melting point of ice, which is 0 degrees Celsius, and then I have to melt it. I'm gonna get 0 degrees water, and then I have to, and I don't have to raise the temperature of the water after that. So the change of the temperature place I only have is where the ice is heated, so that is delta T right here. And then this process is the melting one. So there's where the melting happens. So how much heat will I need in this case? The heat is equal to, when you change the temperature, it's going to be MC delta T. And in this case, C of ice. So I'm going to use I for the ice. And then for the next one, process, that's this process. And then for the next one, to turn it into the water, I'm going to have MH, and it is fusion. So now if I plug in the numbers, I can take mass again out. And I'm going to have C of ice delta T plus H of fusion for water. So the mass is 0.1, and then specific heat of ice they give you, which is 2060. The temperature change, we went from -20 to 0, so the temperature change is 20. And the heat of fusion for the ice is 3.310 to the 5th. Now, if we use a calculator, we're going to get 37,120 joules, or I can write it as 37.12 kilo, which means 1,000 joules. In this question, they give you 200 grams of water at 60 degrees Celsius. So I know the water is already at 60 degrees Celsius. And they want you to bring it to a steam of 140 degrees Celsius. So at first I need to bring the water to the boiling point, which is 100 degrees Celsius. Then I'm going to melt it. So let's look at the processes. So here we're going to have change of the temperature. So I'm going to use C delta T formula. Here we're changing the state. So this is the vaporing process. So that is vapor. And when we vapor the water and we get steam, we still get steam at 100 degrees Celsius. So when we change the state, again, we don't change the temperature. And then when we go from steam to 140 degrees Celsius, then there is the change of the temperature is happening. So now if we write with the formulas how much heat we will need in this process, we have the first one where the temperature changes. So that's going to be MC delta T. And then in this case, the specific heat of water. Then the next process is the vapor. Temperature doesn't change. So it's going to be the mass and H of vapor. And in the next process, so that was the second one. For the third one, I have the temperature is changing by 40 degrees for the steam. So that's going to be MC delta T, but this one is steam. So now if we plug in the numbers, at first I see that every single one of them has the mass. So I can take the mass out. And the mass is 200 grams, which is 0.2 kilograms. So I took it out. And inside of the parentheses, I'm going to have specific heat of water, 4200. So that's specific heat of water. Change of the temperature is 40, so times 40. Plus, I took the mass out, so I only have the H of vapor, which is 2.2 10 to the 6. So specific heat of vapor is 2.2 10 to the 6. And usually on the test, you're going to have all these numbers given to you. And then I have the mass is already taken out, so I only have this part, specific heat of steam. And the specific heat of steam is 2020. So I have 2020 times 40. Now, plugging this into my calculator will give me, so I have as my answer is 489. So the answer is 489 760,000. So it's 760, and I'm gonna write kilojoules. So I could write 489,760, or I can do 489.76 kilojoules. So in this question, I have an ice, 0.3 kilogram, and I'm starting at negative 30 degrees Celsius. And in order to melt ice, when I add heat, so I'm going to be adding heat until the temperature of the ice is going to increase. So I have the change of the temperature in this case, and I still have ice in this process. And then when I get to the melting point, my ice is going to start melting. So I can, any heat added into ice is going to be melting that ice. So here I have the melting process. And there's no delta T, no temperature change. So that's going to be where I have the heat of fusion. Then when I get the water, any heat added to the water until it starts boiling is going to change its temperature to the boiling point. When I get to the boiling point, no heat added to it will change its temperature. Any heat added into the boiling point water will turn it into the steam at 100 degrees Celsius. So here I have the vaporing process or change of state. And then again, when you turn all of it into steam, it is now steam at 100 degrees Celsius, and any heat added into the steam will turn it into another steam at higher temperature, so the temperature will change to 130 degrees Celsius. So when I do the calculations, how much heat do I need to take ice at negative 30 degrees Celsius and turn it into the steam at 130 degrees Celsius? I'm gonna write it as this type of processes in between. So change of the temperature of the ice, I have MC delta T, and this one specific heat of ice, plus melting point. So for this process, I have melting, so that is MH of fusion for the ice. For the next process, the temperature does change. So I have MC delta T, and here we have water. And then for the next process, it is the vapor one, so that's MH vapor. And then for the last one, the temperature does change, so that's MC delta T, and this one is steam. So again, every single one of them has mass, so I'm gonna take the mass out from all of them. So all the mass is gonna be out, so the mass is 0.3 kilogram. So that's 0.3 is out, and what's left inside, I have the specific heat of ice, so that is 2060, and the temperature change here is 30 degrees. Then I have the heat of fusion for ice, which is 3.3 10 to the fifth, so that is 3.3 10 to the fifth. Then I have specific heat of water. For specific heat of water, I'm gonna round it to 4200, and the temperature change is 100. Then I have heat of fusion. So the heat of fusion right here is heat of vapor. So heat of vapor is 2.2 10 to the 6. And for the last part, I have the specific heat of steam, which is 2020. And the change of the temperature is the 30 degrees to go from 100 to 130. So that is 30. Now, if I plug this all into my calculator, I'm gonna get the heat needed to turn negative 30 degree ice into 130 degree Celsius steam equals to, and I get approximately 9.41 10 to the 5th joules. So this is how you would use the heat of fusion and heat of vapor needed when the stages of the matter is happening. Otherwise, every time you have the change of the temperature, you use the old formula MC delta T. I'm going to do a few more examples in this video, Some of them related to this topic and some are not. So I'm just going to do like a review for you, so before you take the test you feel more comfortable about the topic. So here is an example that you have 0.1 kilogram lump of molten lead is at its melting point. So its melting point is 320 degrees Celsius and dropped into 0.1 kilogram of water at 20 degrees Celsius. And they ask you what is going to be the temperature of the water when the lead becomes solid. So at first I need to do the change of state. So at first lead it's molten, it's melted, and when you drop it in the water, it's going to give the heat to the water. So the water's temperature is going to increase, and at the same time the lead is going to be losing some heat. So I'm going to see how much heat is lost by the lead first. And the heat that lead is losing is MH fusion. So if you were melting lead, this is how much heat you would need, and this is how much heat you lose in order to turn it back into the solid. So the mass of the lead is 0.1 kilogram, and the heat of fusion for the lead, so here I see the heat of fusion for lead is equal to 210 to the 4th. So I'm gonna say that is times 210 to the 4th. So that will give me 2000 joules. So that's how much energy lead is gonna lose. Where will this energy go to? This is the energy that goes into the water. So the water's temperature is gonna increase. By how much will the water's temperature increase? And by the way, when the lead turned into solid, it was change of state. Temperature did not change. So the lead is still at 320 degrees Celsius now, but it is just in solid state. So now all this heat, 2000 joules, so this heat went into the water. And I want to know by how much the temperature of the water is going to change. So that's going to be MC. And this one is the water, delta T. So initial temperature of the water is 20 degrees Celsius. And this will tell you by how much that temperature is going to increase. So I have 2000 joules of heat is coming from lead into the water. The water's temperature is 0.1 kilogram. In specific heat of water, I'm going to round it to 4200. And from here, I can calculate how much temperature it increased or changed. And so now if I calculate delta T, that is equal to 4.76 degrees Celsius. So the new temperature of the water when the lead is at solid state and at 320 degrees Celsius, so the new temperature of the water is going to be by 4.76 degrees more than it was initially. And initially it was 20 degrees Celsius. So the new one is 24.76 degrees Celsius. And so the next question is, the first one they ask you was the temperature of the water when the lead becomes solid. So that will be your first answer. That is 24.76 degrees Celsius. And for the next question, they ask you, so that was the first one. And then for the next one, they ask you, what is the thermal equilibrium temperature for both of them after they stay together for a while? So for equilibrium temperature, I have to use this formula right here. So it's Q1 plus Q2 is equal to 0. So it's going to be Q1 plus Q2 is equal to 0. So the heat that is going to be, the lead is going to be losing now is going to go into the water. And finally, they will reach the equilibrium temperature. So now if I have MC delta T, so for both of them it's going to be Q MC delta T because the temperature is changing. So I have the mass of the lead, C of the lead, and delta T of the lead, or I can say final minus initial or equilibrium temperature. So that's going to be equilibrium temperature minus the initial temperature, which is 320 degrees Celsius, plus I have the mass of the water, C of the water, and then I have the equilibrium temperature minus initial temperature. So this one for the lead, this one is for the water, and all of that is equal to 0, and that is this temperature. So now plugging in my numbers, I have the mass of the lead is 0.1, specific heat of lead. So from my data from the tables, I see that lead is 130. So I'm gonna plug in 130. And final temperature, I'm just gonna keep it T for now. Minus 320 is initial temperature of the lead, and then plus 0.1. Specific heat of water is 4200. And then the final temperature of them both minus initial temperature of the water, which is 2476. And that is equal to 0. So if I do my calculations here, I have 130 times 0.1 gives me 13. And then I have T minus 320. And then plus 0.1 times 4200 gives me 420. And then I have T minus 24.76 equals to 0. I'm going to distribute 13, and I'm going to distribute 420, and then I will combine or add them together. So I'm going to add wherever I have T right here, 13T plus 420T. That gives me 433T. And then 13 times 320 and 420 times 2476 will give me 4160, and minus the other one, 103.99.2, and all of that is equal to 0. So now solving for T, I have, it is 14,559.2 divided by 433, and that is equal to 33.6 degrees Celsius. So the final temperature of both after they reach equilibrium is going to be equal to 33.6 degrees Celsius. So that was a little addition to our thermodynamics and heat lessons. And if you have more questions about the problems that you see in our lessons, please email me or let me know during our class times. And thank you for watching, and I'll see you in the next video.